right, welcome back, everybody. So we're going to go over the homework, and then we'll get into section 11.3. Sound good? Again, just to kind of go over a couple of things. Quiz Thursday of this week. Tomorrow is the U.S. history test, so you guys don't have a test tomorrow. You get a little bit of a late start tomorrow, so that means there's short periods tomorrow and Wednesday. Remember that tomorrow and Wednesday, both short periods, which means that we're just going to review for our quiz that's going to come up on Thursday. Tomorrow, you'll be getting a practice quiz and get some time to work on it. We'll basically go over this 11.3 homework. I'll give you the practice quiz, and we'll go over it on Wednesday, and then on Thursday we'll have our quiz. You know how we normally don't have homework after quizzes? This is one of the exceptions where we will have homework over the night of a quiz. Just basically, I'm going to ask you to do a practice test, practice OST test, and then we'll go over it on Friday, and then we're going to do another one over the weekend, and we'll go over it Monday, and then we'll do another one on Monday night. We'll go over it on Tuesday during that late start. Remember, not tomorrow, but the following Tuesday, that's when we have our Algebra 1 test. So, you should be ready for it. It shouldn't be too bad. All right, so let's start going over the homework. Number 18 here. If a golf ball is dropped from a height of 27 feet, the function f of x is equal to 27 times 2/3 to the x gives the height in theta after each bounce, where x is the bounce number, the number of times it's bouncing. What will the height of the fourth bounce be? Hey, Doretta, what do you think? 5.3 feet. Good, I like that. Oops, that's not a pen. 5.3 feet. The book says 5 1/3 foot, or 5.3 feet. That's good too. Notice again a couple things about the exponential function. This gives you the starting value, just like we had the starting value in the geometric sequence, a sub 1. This gives you the starting value, and this actually gives you what? What is this 2/3 referring to? What is that 2/3? What value is that? Okay. Good, that's how much it's going up or down by, how much I'm continually multiplying by. And the fact that it's a decimal, the fact that it's less than 1, the fact that it's a fraction, is telling me what's happening with my sequence. Going downward, right? I'm multiplying by 2/3. It's getting 2/3 the size each time that bounces. All right, same thing with 19 here. Suppose the depth of a lake can be described by the function 334 plus 0.976 to the x, where x represents the number of weeks from today. Today, the depth is 334 feet. Again, they didn't need to tell you that piece of information, right? That piece of information you could have gotten from the equation. The original amount, the starting value is 334. 0.976 is my R value. And because it's 0.976, what's happening to the depth of the lake? It's getting smaller and smaller and smaller. So honestly, all I do is take 334 times 0.976 to the 6th power. Let me pull a name here. Let's see. Who's the lucky one? Is that Thursday? There you guys. Ben, what would be my answer there for 19? 290.3. I got 289. Well, at least that's what the book gives. I wonder what. You got 289, 334 times. Maybe you just mistyped it to the 6th power. Yeah, 289. Or just round it to the nearest whole number. That's why 289. 289 feet. So that's telling me that within those 6 years, that's how much it's going down by. Starting at 334, it's going down to 289 in 6 years. A ball rolling down a slope travels continuously faster. Suppose the function 1.3 times 1.41 to the x describes the speed of the ball in inches per minute. Take a look here, folks. Because that's a 1.41, it didn't need to tell me that the ball was going to get faster, because 1.41 is going to tell me that my exponential function is going to grow, right? It's going to get bigger. The speed is going to increase. How fast would the ball be rolling in 15 minutes? Okay, so what would it be, Serenity? What would it be, Serenity? 20. Good, 225. They said 0.02, but I would be fine. It said round to the nearest hundredth, but I would be fine with 225. Now, that being said, inches, right? Suppose the function describes the speed. Inches per minute. Yeah. That's the label there. Now, what I was saying before, if the problem on your OST test would have said, round to the nearest 100, it might get picky. Like they might be picky about that. So please, please, please watch what they're asking it around to. For my purposes, in my class, I really don't care. As long as you have the right answer, I'm good. Okay. Now, tell whether the ordered pair satisfies an exponential function and explain your answer. Rosalie, is this exponential for number 21? Oh, you didn't do your homework, did you?
Yeah.
No, you didn't. All right, so hold on. We got to make ourselves a table. -2, 9, -1, 3, 0, 1, 1, 1/3. Now, Rosalie, is there a constant change in my x values? Look at your x values. Are those constantly changing? Good. It's going up by 1 each time. Now look at my y values. What's happening with my y values? What's my ratio? No, not 3. No, not -3. What am I multiplying by?
Oh.
What am I multiplying by for my y values? 9 times what is 3? What do I multiply 9 by? How do I figure this out? What do I do to 9? To get it over to the other side. So 3 divided by 9. What is that? 1/3. Let's say 1/3. Yeah. It's 1/3 as my R value. Yeah. So does that carry through? Yeah. So can we say that this is geometric? Yeah. So we can say that this is exponential. And looking at 22, Nate, is that exponential?
I said no.
You said no. I would agree with that. Let's take a look here at my table. -1, 0, 0, 1, 1, 4, 2, 9. If I'm going from here to here, well, take a look at from here to here. That would be 1 times what is 4? 1. I'm multiplying by 4. Is that the same case here? No. So I can see it right from there. But look, if you ever have a 0 times anything is just going to get you back to 0. I'll say this. Think about this. Does any exponential function run through 0, 0? No. It will never run through the origin. Because if I want to be continually multiplying, anything times 0 is going to get me stuck on 0. 0 times anything is going to get me back to 0. So it will never get away from 0 if it runs through the origin. So therefore, if it runs through 0, 0, it's not going to work. Okay. So no, that this is not exponential. It's not even linear either. It didn't ask it, but let's take a look real quick. Is there a constant change? No, this is going up 1. This is going up 3. And this is going up 5. But you know what this is, actually? Everybody take a look up here. You know what this is? What does that tell me that this function is? Not linear. If this was all the same, this would be linear. But because this is a constant set of second differences, what does that tell me? It's quadratic. It's quadratic. Okay? It's a U shape. It's a parabola. Right? If you have a constant set of second differences, that tells you that the function is quadratic. Did it ask me for that? No, but that's what it would be. All right, so here, we're going to take a look. You know what, let me just get rid of these blue boxes. Everybody take a look at your graphs for 25 and 27. Okay, not only look at your tables, but look at your graphs as well. Now, these are the graphs provided by the book. So I know that, like, taking a look at number 27, I know the numbers got really big. You could just kind of make it whatever you needed to on your graph paper. I'll give you a minute to look at those. Any questions on 25 or 27? Okay. And then let me scroll down so you can see 29 and 31. Honestly, these should have been pretty easy for you guys. All you're doing is just plugging in numbers. They're either going to get really big really fast or really small really fast. All right, so now we're going to get into section 11.3. I'm going to have to modify the guided notes a little bit. I had put something in the guided notes that we're not actually going to do, and I had accidentally omitted something that we are going to do, so we're going to have to modify them a little bit, and I'll explain it as I go. De nada. Yeah. I'm good now. Okay. Today we're going to add on a couple more equations to our list. Okay, we're going to add on a couple more equations. We're going to add on 3 more equations to our list. Now remember on this quiz on Thursday, the first part of your quiz is going to just be formulas. Okay, the first part of your quiz is going to be just formulas. And the second part of the quiz is going to be application of those formulas. So what's going to happen is, again, I know I've said this before, what's going to happen again is you're going to do the first part of your quiz, and then I will come around and check that beginning part, and I'll grade that beginning part as you're sitting there. And then if you, basically after that, you're going to know the formulas so that you can use the correct formulas after beyond that. So let's talk about the new formulas that we got. I've been using the terms exponential growth and exponential decay as we've been learning exponential functions. Remember, exponential growth is going to get big fast. Exponential decay is going to get small fast. It all depends on your R value. It all depends on how what your R value is, whether it's bigger than 1 or whether it's less than 1. You can call it exponential growth or exponential decay. Exponential growth occurs when a quantity increases by the same rate, R, in each period of time, t. When this happens, the value of the quantity at a given time can be calculated as a function of the rate in the original amount. So this is our formula. Again, box it, circle it, do whatever you need to do. This is exponential growth. This is our exponential growth formula. It's y equals a times 1 plus r to the t. A times 1 plus r to the t power. Now, analyze what we've got here. Our A, that beginning, that thing, the first letter that you see, what is A? What's always the number that's sitting right out in front of the function? It's always the beginning term. It's always the starting value, right? We saw that within our arithmetic and geometric sequences and our exponential functions, right? It's always that beginning value, the starting value. Where am I beginning from? Where's my y-intercept? That's the same thing. Now, take a look at this 1 plus r. R is obviously my rate of increase or decrease. Usually in these word problems, it's given you as a percentage. So like population is growing by a factor of 13%, or decreasing by a factor of 13%. Or maybe a growth of bacteria is growing by a rate of 20%, right? That percent you're going to use applied as a decimal. Now look what we're doing here. We're adding 1 to it, which is interesting here, because if it's bigger than 1, it's got to be growth, right? If it's bigger than 1, the sequence must get bigger and bigger and bigger, right? That's what we've been saying about our R value all along. If we make that R value something bigger than 1, the sequence is going to grow. So that's interesting that we have a 1 plus R raised to that power. And t is the time. Okay. T is the time. And that time period is all dependent upon, whether it's years or months or days or hours or whatever. And I'll have to tell you within context of the problem. So let's take a look. The original value of a painting is $9,000, and the value is increasing 7% per year. Write an exponential growth function to model this situation. Did I need to tell you to write a growth function? No. The context of the problem says the value is increasing. So at that point, see, I'm going to start omitting things that the test wouldn't give you. Like the OST test would never tell you, write an exponential growth function. It would just say, write a function to model this situation, right? it'll just say write a function to model this situation. Well, it's growing by a percentage per year. That's exponential growth. Okay, so what we can do here is say, well, if it's exponential growth, it's y is equal to a times 1 plus r to the t power. That's our general formula, right? What's my starting value? What's my a? Liam, what's my a?
The original amount,
Which is
$9,000.
$9,000. Every time I see your eyes close, I'm like, oh. And then the value is increasing by 7% per year. What's my 7% as a decimal? 0.07. Watch out for that. Remember, if I've got 7%, that's taking that decimal and moving it over here. That's 0.07, right? If you say 0.7, that's 70% growth. Buy me that painting. I love 70% growth. So 1 plus 0.07. Well, I can just make that 1.07 raised to the t power. So there's my function. It says write a function to model the situation. Done. Then find the painting's value in 15 years. Well, that just means I got to plug in 9,000 times 1.07 to the 15th power. So $24,831, let's say to the nearest cent, and 28 cents. 24,831.28. And that's it in 15 years. So essentially, we're doing the same thing that we were doing last week, right? But now we're like writing the function based on the information that's given. All right, a sculpture is increasing in value at a rate of 8% per year. And its value in the year 2000 was $1,200. Write an exponential growth function to model the situation. Then find the sculpture's value that it would have been in 2006. All right, so go ahead and write the function. Practice it. Do it. All right, so the value, the original value, remember the function is y is equal to little a times 1 plus r to the t power. Well, that means that my value is $1,200 times 1 plus what? 0.08. Don't say 0.8, 0.08. You know, sometimes I say this 1 plus 0.08 to the t, but honestly, isn't that just 1,200 times 1.08 to the t power? You can write the plus in there, you don't have to. It essentially gets you the exact same thing. Right? You're just tacking on the percentage to your 1. Because again, you want it to grow. If you had only said 0.08, that function's going to decrease. That's going to decay. But we want it to grow instead of decay. Growing at that rate. 1,200 times 1.08 raised to the 6th power. In 2006, it's going to be 1904.25. 1904.25. That's the value after 6 years, growing at a rate of 8%. Not too bad, right? And the only difference between the exponential growth function and the exponential decay function is that one is going to increase and the other one is going to decrease. You know, before you look at the formula, the only thing that's going to change should be, instead of a bigger than 1 number, it's going to be less than 1. So exponential decay is going to be essentially the exact same formula, but instead of a plus, it's a minus. Okay? Instead of a plus, it's a minus. All of the parts remain the same, but now the only thing that's different is the operation in the parentheses. Why? Because now we have to make that base, we have to make that thing that we're raising to the power, we have to make that thing less than 1, because we want it to go down, not up. Okay? So instead of 1 plus r, it's just 1 minus r. So essentially, it's the exact same equation, just with a different operation. Notice an important difference, obviously, is the subtraction sign. Okay, I talked about that already. The population of a town is decreasing. The population of a town is decreasing at a rate of 3% per year. Again, I could take out from this question, I could take out, write an exponential decay function. I could have, like the OST test is just going to tell you this. Write a function to model the situation. You have to know that it's going to be exponential decay. And then you have to plug this stuff into the formula. How do you know that it's exponential decay? Well, it's decreasing by a percentage. If it's decreasing by a percentage, that's exponential decay. So I start, again, let's write our formula out. Y is equal to A times 1 minus R to the T. Why do I know that it's minus? Because it's decreasing. Because it's decreasing. All right, and it's decreasing at a rate of 3%. In the year 2000, there were 1,700 people in this town. Now, I'm going to encourage you to write out the 1 minus. 1 minus what? 0.03, not 0.3, 0.03 raised to the t power. Now, I like to put this equation, 1,700 times, I like to actually do this, 1 minus 0.03, so it's 0.97. I like to put that in there just to remind myself, okay, that's less than 1, that's going to go down. There's my function. And then find the population in 2012. So what's my t value? 12. So let's plug it in. Let's say 1,700. 1,700 people in the town. It's decreasing at a rate of 3%. And I'm going to raise it to the power of 12 to see how many people are going to be there in 12 years. 1179.53. 1179.53. Now, I know we're talking about 0.53 of a person, but again, we're predicting something that could possibly happen, not actually talking about concrete numbers. I know we were talking about future and past, but when this book was written, it was talking about future, because this book was written in 2008. Yeah. Well, I know. But I think they're still considered a whole person. One mind, one soul. There you go. All right. The fish population in the local stream is decreasing at a rate of 2.5% per year. The original population was 48,000. Write an exponential decay function to model the situation. Then find the population after 7 years. After 7 years. All right. So again, I shouldn't need to tell you to write an exponential decay function. Why? Because I see a percentage and it's decreasing. Decreasing by a certain percentage. All right, so I know that the formula is y is equal to a times 1 minus r raised to the t power. And I can take my original amount, my 48,000, multiplied by 1 minus what? Not 2.5, not 0.25, 0.025. Be careful there, folks. 2.5%, I've got to move the decimal 2 places. It's here, once, twice, 0.025. 1 minus 0.025 to the t power. Be careful when moving your decimal places. That's the only tricky part to this. 48,000 times, I haven't done the 1 minus. I'm sorry, 1 minus 0.025, and that is 0.975. So 48,000, this is y is equal to 48,000 times 0.975 raised to the t power. And now we're going to say 48,000 times 0.975 raised to the 7 years, 7th power. 40,204.4. 4204.4. 4204.4. Questions about that? Okay, so these two formulas that we added on today, they're essentially the same formula, right? They're essentially the same formula. They have the same things in it. The only difference is the plus and then the minus. Now, you guys can flip your page and you see this thing called compound interest. Okay? Yeah, looks gross, right? Let's cross out that whole page.
Okay. The whole thing?
The whole thing. We're not going to do compound interest. So flip it over onto the back where there's a blank page. See what happened was? There's two major applications of exponential growth and exponential decay. And one of them is compound interest. Guess what? Compound interest doesn't show up on your course test, so we're not going to do it. But you know what does? Half-life. And it's kind of good because half-life is a lot easier than compound interest. So, but the problem is I omitted it from the guided notes, so we have to write it.
All of it.
I'll highlight what you need to write out. A common application of exponential decay. Now, half-life. Have you guys studied half-life? Some of you maybe yes, no. Okay, so half-life is basically this. You've got any sort of substance and everything is constantly decaying. Any non-living substance, any non-growing substance is constantly decaying. Everything in the world. Even like the desks that you sit. Everything is constantly decaying. There are things acting on all of the substances around us that make it break down, right? Everything has a decay rate, right? Now, what half-life is it's saying, okay, how long does something take to decay down to half of the original substance, down to half of the original value? And each thing, each substance, each compound has its own rate at which it will decay down to half of its original value. Some of the stuff is really, really long. Like it takes like 80,000 years for it to decay down to half of its original value. But some is really quick. Like some values are really quick, like certain compounds, certain like radioactive things, certain isotopes, they will decay really quickly down to half of its value. Okay, so you gotta act right away. You gotta be very quick about what you do with that. So half-life is this thing where, okay, you can measure however long, 50 years, 100,000 years, I don't know, whatever. It's different for everything. How long does it take for, you've got 10 grams of this thing? How long is it going to take to get down to 5 grams? Because that length of time is going to be the exact same length of time for the 5 grams to go down to what? 2.5 grams, half of its remaining value. And then that 2.5 down to 1.25, and that down to this, and so on and so on and so on. Okay. So what a half-life value is the amount of time it takes to get down to half of that remaining thing. Now, think about it this way. Does, at the end of a certain half-life, does like half of the chunk of whatever that is just like fall off? Like disintegrate, like, just like flake off into thin air? No. It's constantly decaying, right? The world around is constantly acting on it. So it's just kind of like, we don't even see the change until you notice it about halfway through, or about a full way through the half-life cycle, half of that substance still remains. So thinking about it as exponential decay, we're still going to have this beginning amount, but it's going to decay. Now, how much is it going to decay down to? Half of its original value. So you know what replaces the 1 minus r? 0.5. Okay, 0.5. So this is what you need to write down. I would write down this entire box, actually. Okay, and all of the pieces in it, so that you know what it is. They're changing up the letters, but essentially it's representing the exact same thing. So we've got half-life. It's A is equal to P, my starting value, times 0.5 raised to the T. The pieces of the function are not changing. They're changing up the letters, and I don't love that they're changing the letters. But half-life is modeled by the equation P, which is our starting value, times 0.5. Why 0.5? Because again, it's half-life. Okay, that's easy to remember then. raised to the t. Now, that t value can be a little tricky. It's not just saying the number of years. It's saying the number of half-lives in that given time period. The number of half-lives in that time period. So which means that, like, if this substance has a half-life cycle of 2 years, and I want to know what's going to happen in 6 years, how many half-life cycles did it undergo? 3 total half-life cycles. If I want to know what it's going to be in 20 years, how many half-life cycles did it undergo? 10. So 10 would be your t-value, right? So that number of half-life cycles that it takes within that time period, that's the t-value. You don't just write the time, right? I don't just say, okay, in 20 years, 20 is my t-value. No. It all depends on how many half-life cycles it undergoes. Okay. Anybody still need that on the board? Okay, let's do a word problem here. Now, you don't need to write down the whole word problem. Just kind of make notes for yourself there. Solve it with me here. So example 1a, this substance, astatine 218, has a half-life of 2 seconds. So this must be some radioactive isotope. It's got a half-life of 2 seconds. Find the amount left from 500 gram sample of astatine 218 after 10 seconds. After 10 seconds. All right. So my formula is A is equal to P times 0.5 raised to the t power. Let's identify the values here. A is your final amount. A is your amount left over after that time period. But what is my beginning amount? What is my P value? 500 grams. Okay, and what's my T? 5. It's not 2 seconds. It's not 10 seconds. It's how many half-life cycles? Okay, what is the half-life cycle? 2 seconds. How much total time am I going to look at it? 10 seconds. So how many cycles of 2 seconds do I have? 5 cycles. 5 cycles. Okay. How do I come up with that? What's the formula to do that if you'd like one? You take the amount of total time over the half-life. Okay, you take total time over half-life. And that's how many cycles you get. That's the t-value. Okay, for half-life. So that's why, in this case, my t-value is going to be 10 over 2, which is 5. That's why I get my t-value is 5. All right, so let's create my equation. So A is equal to 500 times 0.5 to the 5th power. So 500 times 0.5 to the 5th power. 15.625. A is equal to 15.625 grams. You could round that if you needed to. It was a nice clean decimal, so I wrote the whole thing. This is an example of a geometric sequence. Why? Because each term, I'm multiplying it by half. Each value, half of it remains. Each term in the sequence, half of it remains, which makes sense. So my R value is 0.5, my beginning value is 500, and what term am I looking for? I'm going to look for the 5th value there, starting at times 0, so it's 5 minus 0 would be 5. All right, let's do one more of these. So this other element, whatever, cesium-137. Cesium-137 has a half-life of 30 years. So this is something that's going to take a long time to break down. Cesium-137 has a half-life of 30 years. Find amount left from a 100 milligram sample after 180 years. All right, so let's do this again. A is equal to P times 0.5 to the t power. So again, this thing has a half-life of 30 years. That's how long it's going to take for it to go one half-life cycle. I take a look at it once, I wait 30 years, I look at it again, half of its value is remaining, half of the amount is remaining. All right, so my p-value, my starting amount is 100 milligrams. Now, what's my t? 6. How do I know that? Well, I take the total time, 180 years, divide it by its half-life, 6. It's going to undergo 6 half-life cycles. Because I can look at it, okay, 30 years, if I'm looking at it for 180 years, it's going to go through 6 terms, okay, 6 cycles. So I can say 100 times 0.5 to the 6th power. That's going to give me my final amount. 100 times 0.5 to the 6th power, and that's going to be 1.56. I'll say 1.56. Milligrams. Because one cycle is going to get me down to 50, 2, 25, 3, 12 and a half, 4, 6 and a quarter, 5, 3 and something, 6, 1.56. Good. There's another example down here, but I'm not. Now we're good. We're good. That's good. All right. So we added on 3 formulas today. 2 of them are essentially the exact same thing, right? So those shouldn't be. You're not memorizing really 2 different things. The half-life formula really is essentially very, very similar, but the only difference is instead of a 1 minus r, I've just got, I know it's 50%, right? So it's just going to be 0.5. 1 minus 0.5 is 0.5. All right, so long everybody watching at home.